In this video, we're going to be talking about moments of inertia. In the previous video, we found that moments m sub y and m sub x about the y-axis and x-axis respectively, and we found them and used them to find the center of mass of a planar lamina with a domain D. And these were the first moments. M sub y was the double integral over our domain of x times the density function delta of xy dA, and the moment about the x-axis, m sub x, was the double integral of y times delta of xy dA. Some people use rho instead of delta here. Okay, so we have our density times our x and double integral of that. That's the moment about the y. The density times the y. Integrate that. That's the moment about the x. These are first moments. We can also have second moments by bumping these up to the second power. So the second moment with respect to x would be double integral x squared delta of xy dA. That's the moment of inertia about the y-axis, I sub y. And I sub x, the moment of inertia about the x-axis, is the double integral of y squared delta of xy dA. So we bump this up to second power, we get a second moment. We could talk about third and fourth and fifth moments in a similar manner. But we're going to look at second moments in this video and see what their physical meanings are. And we're going to think of this as a moment of inertia. So we can recall from Newton's second law of motion that force equals mass times acceleration. Because of this, mass may be thought of as the resistance of an object to change in motion in a straight line. You have to apply a force to get it to accelerate or change its velocity in a straight line. And that's proportional to that mass. So the mass is the amount of resistance, you might say, to that change. For a single fixed point mass, its moment of inertia about a line is I equals m times d squared, where m is its mass and d is its distance from the point to the line. So we apply a similar type of reasoning as we have done earlier. If we apply this to a planar lamina, well, what are we going to do? We're going to divide it up into small little rectangular regions, approximate the mass within one of these subregions as the density of the point, say in the center of that region, times the area of the region to get a mass, a point mass, or an average mass, or an estimated mass at least of that little square or rectangular subregion. And then we're going to multiply that by the square of the distance to the line. Now, if we do this for each little one, this is like what we've done before, what we're talking about up here for a point mass. Add those up, and then that's going to give us a moment of inertia. Well, not quite. We want to actually now take a limit as the delta x goes to 0 and the number of rectangles goes to infinity. And now we have a double integral, and that is the moment of inertia. So the I sub y, again, is the double integral over our domain of x squared times the density function dA, and the moment about the x-axis, I sub x, the moment of inertia about the x-axis, I sub x, is the double integral over the d of y squared times the density function xy dA. And these represent the resistance of a lamina to change in a rotational motion about a line. So it kind of relates torque to this. So if we sum the moment of inertia about the y and x axes, we obtain what's called the polar moment of inertia. I sub 0 is I sub y plus I sub x, that is the integral of x squared times the density dA plus the integral of y squared times the density dA, double integrals, which of course, if you look at that, that's just the integral of x squared plus y squared times the density, or r squared times the density. So r, of course, is our polar distance, so that's why this is sometimes called the polar moment of inertia. And it represents the resistance of a lamina that's in the xy plane to a change in rotational motion about the z-axis. Notice that rho here, this Greek letter, is often used instead of the delta. So if we apply this to our example we've looked at in earlier videos, where we're looking at this triangular region where the top is x plus 3 is the density, the bottom is y equals 2x, the top is y equals 9 minus x, the left side is x equals 0, and it goes to this corner here at 3, 6, then the moment of inertia about the y-axis would be x squared times that rho, or delta. So that's x squared times x plus 3, and we integrate there from a bottom of 2x to 9 minus x when we integrate with respect to y first, and then the x's are integrated with respect to them last, so it goes from 0 to 3. I went ahead and distributed here. The moment of inertia with respect to x then is just y squared times that rho, so it's y squared times y plus 3. And the moment of inertia about the polar moment of inertia is just summing those two integrals. Here are the details worked out to get the numbers. When we distribute the x here, we get x cubed plus 3x squared, which we can bring out front of that first integral because it doesn't have any y's in it. So this integral is just y. We evaluate it from the two ends. We're doing 9 minus x minus 2x is 9 minus 3x. When you FOIL this out, some of the terms cancel out, and so you're left with, let's see, the x cubed cancels. So 9 times x cubed is 9x cubed. 3x cubed times a negative 3x is negative 3x cubed, so that cancels out. And what's left is the first and last terms here give us minus 3x to the fourth, and the middle two here give us 27x squared. The other two canceled out. All right, add 1 to the power, divide by the new power. This goes up to 5, divide by 5, that's negative 3/5. Goes up to 3, divide by 3, that's 9. Plug in 3 and 0 here, and the rest is just some arithmetic. The zeros parts are 0, so that's easy. 3 cubed is 27 times 9 is 243. 3 to the 5th is 243, I think, times negative 3 is negative 729, and that's over 5. Get a common denominator of 5 and add those together. You get 486 fifths, or 97.2. That's for the moment of inertia about the y. The x is a little, moment of inertia about x is a little harder to work out. You have a y square here, so when you bring you can bring the x minus 3 out front of the first integral, but you're doing the integral of y squared. Again, not too much trouble here. The power just goes up 1 divided by the new power. So it's 1/3 y cubed. When you plug these in, you get 9 minus x cubed minus the 2x cubed. 2x cubed is pretty easy. That's just 8 times x cubed, so it's minus 8x cubed there for the end. When you cube this, it's a little harder. Cube the first term is 729. That turns out the next term is, let's see if we go from the back here, it's the first term squared times the second term times 3, which is, let's see, let me start with the x. Minus x, you cube it is here. 3 times the 9 times the x squared is 27. Then 3 times the 9 squared times the x is 243, which is what I've got there. And then the last term is the 9 cubed, which is 729. Okay. Combine like terms by taking the negative 8x cubed plus the negative 1x cubed, you get negative 9x cubed. I'm going to factor out a negative 9. Negative 9 times the 1/3 in the front is a negative 3, so I'm just dividing all these terms by negative 9. Negative 9 divided by 1 is negative 9 is positive 1. 27 divided by negative 9 is negative 3. Negative 243 divided by negative 9 is positive 27. And 729 divided by negative 9 is negative 81. Alright, now we need to multiply this out. X times the x cubed is x to the fourth. x times the negative 3x squared is negative 3x cubed. Then we got 3 times that x cubed is 3x cubed, so that cancels out completely. The x squared term, I got 3 times negative 3, so it's negative 9x squares, and that times that is 27x squares. 27 minus 9 is 18, so that's x squares. The x should be canceling out. Let's see, 3 times 27 is 81x, and then the x times the negative 81, that's negative 81x. Those cancel out. And 3 times negative 81 is negative 243. We still got our negative 3 along for the ride. Find an antiderivative by adding 1 to the power divided by the new power. This goes to 5. Divided by the new power, 1/5. That goes up to 3. 18 divided by 3 is 6. 243 picks up an x. Evaluate from 0 to 3. Plug in the 5. Plug in the 3. Where the x's are, plug in the 0, subtract. And then at the end, multiply by negative 3. These three terms at the end will come out to be 0. 3 to the 5th is 243, and that's over 5. 3 cubed is 27 times 6 is 162. 3 times negative 243 is negative 729. Add those together and then multiply by the negative 3, you get 7,776 over 5, or 1,555.2. That's the exact value. Add those two together in fraction form, that's 8,262 over 5, or in decimal form, that's 1,652.4, which is the moment of inertia about the pole. Polar moment of inertia. All right, that's moments of inertia.